Okay, so that was like the basic geometry and local well-posedness of the system. And now I want to get far beyond local well-posedness and talk about singularities. And as I've hinted at, it's a very rich and rapidly developed and rich in 1+1 settings. And that, certainly I think that's where we should start. You can gain valuable intuition by about geometry and shock waves by studying isentropic plane symmetric solutions. Okay, so what are these? By definition, these are solutions that depend only on t and x1. Okay, it could be any other space variable. I just chose x1 for convenience. And isentropic means that the entropy variable is constant. So that's kind of like saying you don't have to worry about thermodynamics or temperature. And just for convenience, I'm putting the entropy equal to 0, but there's nothing special about 0. Any other constant would work. And we're going to assume that the 4 velocity has only 2 non-zero components, u0 and u1. So we're going to forget about u2 and u3. And it turns out that you can think of these as like that these conditions are propagated by the flow if they're satisfied at time 0. So in other words, if you assume this is true for the initial data, then the solution will respect these properties as well. Okay, so that's an exercise that can be, that's not a difficult exercise. You can basically derive energy estimates for these quantities, showing that if they're initially 0, then they're always 0. Okay, or equivalently, as it turns out, that this is just another way of saying that you're studying an isentropic fluid in 1+1 dimensional Minkowski spacetime. It's a totally equivalent way of thinking about things. Okay, so let me introduce some null vector fields for you in this setting. So by this setting, I mean 1+1 dimensional, and isentropic, and plane symmetric. Okay, so here are 2 vector fields, which I'm calling L and L bar to sort of coincide with your intuition from these, as it turns out, are null vector fields written down explicitly. These are null vector fields with respect to the acoustical metric, so this metric G that I introduced earlier. And the fact that you can explicitly write down these formulas and study the solution, study shock waves using these explicit formulas, this is very special to 1+1 dimensions. If you try to study similar problems in higher dimensions, you cannot explicitly write down null vector fields that have the properties that you want. There's something very special about 1+1 dimensions, that these vector fields are explicitly given to you in terms of the solution. Okay, and so there's like an algebraic connection between these vector fields L and L bar and the acoustical metric G that I introduced earlier. So more precisely, if you take the acoustical metric G and you rescale it, so actually we're looking at G inverse, and you rescale it by dividing by G inverse 0, 0. So this makes the rescaled tensor has a 0, 0 component equal to -1. That's how you should think about this rescaling. Then you get this nice formula. This is what in 1+1 dimensions. You could also think about this as an acoustical metric on the 1+3 dimensional space-time by adding on the dx2 squared plus dx3 squared part, which I'm not writing here. Okay. So this is just a way to show you that there is a connection between, an obvious connection between these 2 null vector fields and the acoustical metric that I introduced earlier. And so basically, it's exactly this formula that allows me to call them null if you want. These 2 vector fields, because of this formula, are rightfully callable null vector fields by this metric. Okay, their length is L and L bar have length 0 as measured by G. Okay, so you can do a lot with these explicit formulas, plus one other ingredient, and that other ingredient is the Riemann invariance. So these formulas that I'm writing, they're a little bit unwieldy to write these details. These details are actually not that important. If you want to read about these details, let me find so I had a link, which maybe I can post in the chat. I'll do that at the end. You can read about the derivation of these Riemann invariants and these vector fields L and L bar. You can read about them in the paper by Christodoulou and Lizabach on what they call the spherically symmetric shock development problem. So I'll say more about the shock development problem later in the course. That's basically the problem of extending the solution weakly past the shock singularity. And in that paper, they do all kinds of detailed calculations about the Riemann invariance and these null vector fields. And you can find everything you want there, with one small difference. In their paper, they're looking at spherically symmetric solutions so that they have powers of R, the radial variable, floating around all over the place. And because I'm not looking at radial symmetry, but rather plane symmetry, I don't have those powers of R. So things are in fact even simpler. Okay. So you can introduce this quantity called zeta, and I'm trying to use the notation of Christodoulou-Lizabach. Maybe I've changed the signs a little bit to make the presentation look nicer. And zeta can be thought of as a function of U1 because of the four velocity normalization condition. And then there's this other function that I'm just calling capital F, which is an ODE solution to the equation that its derivative, F prime evaluated at H, should be 1 over H times C. So here H you can think of as the enthalpy, and C, to make sense of this formula, you have to think that C should be written as a function of H, which you're basically allowed to do in the sense that in the study of relativistic fluid mechanics, you can, because of the thermodynamic assumptions, you can kind of go back and forth between any of the fluid variables that you want. Like you can use pressure, you can use enthalpy, you can use density, they're all sort of, everything can be written as a function of everything else, if you know what I mean. Okay, but in any case, once you have defined these functions F and zeta as follows, then you can introduce the famous Riemann invariance. There are two of them, R plus and R minus. And according to my conventions and my sign conventions, this is how they're defined. R plus is F plus zeta, and R minus is F minus zeta. And because of our positivity assumptions on various thermodynamic quantities, you can actually, in principle, invert these relations and solve for H and U1 in terms of R plus and minus, at least in a neighborhood of this constant state where H bar is some non-zero constant. So in other words, you can use, if you're studying simple isentropic plane wave solutions in 1+1 dimensions, or if you're, sorry, not simple, I haven't said simple yet. If you're studying isentropic plane wave solutions in 1+1 space-time dimensions, you can choose your unknowns to be H and U1, or you can choose them to be R plus and R minus, and they're completely equivalent, okay? And it's very advantageous to use R plus and R minus as the unknowns. And here's why. So again, you can, I refer you to the Christodoulou-Lizabach paper on shock developments and spherical symmetry for the details behind some of these calculations. And in there, again, in their paper, there are powers of R because they're in spherical symmetry. Okay, but in our setup, here's the statement. In isentropic plane symmetry, the relativistic Euler equations are equivalent to the following system of quasi-linear transport equations. The L derivative of R plus is 0, and the L bar derivative of R minus is 0. Okay, this is why the Riemann invariants are so nice, and this is why the vector fields L and L bar are so useful, because it basically doesn't get any simpler than this. This shows a very sharp separation of 1 + 1 dimensional fluid flow into, if you want, let's call this a right moving wave, and the other one, let's call it a left moving wave. Okay, this is, you can't possibly hope to sort of have a better setup for the study of shock waves than this. Okay, so here's the key point. Let's remember, here's what L and L bar look like. They're normalized so that the rectangular dt part has a coefficient of 1, and then there's the coefficient of d1. And the point is that you can write, in principle, these coefficients in terms of the Riemann invariance. So that's what this slide portion here says, that there are functions f and f tilde, whose details at this level simply don't matter at all, such that L is dt plus a function of the Riemann invariance times d1, and L bar is dt plus a different function of the Riemann invariance times d1. Okay, and so that's why this is a quasi-linear coupled system. The right-hand side doesn't tell you about the coupling. It's the coefficients that tell you that there's coupling. Okay, so this looks like a simple system, and but it's surprisingly rich. Okay, and it's even with further simplifications, it's surprisingly rich. Let me go back one slide. If you take initial data so that R minus is completely 0 at time 0, say, then that will be propagated by virtue of this transport equation. And therefore, R minus would remain 0 for all time. That's called a simple wave. This is a simple wave. You study solutions where only one Riemann invariant is non-zero. So this is the most simple possible form you can get the equations in. Then the Cauchy problem for relativistic Euler flow is just the L derivative of R plus is 0. And the initial data are, let me call them R with a ring over top. And because the other Riemann invariant R minus is 0, I'm not even going to write it. I'm just going to take the point of view that the vector field L is like dt plus some function of the unknown times d1. And the whole point of this, of course, is that this is a Burgers type equation. In basically great generality, you should expect that singularities will form in solutions. Okay, you can already see this for these so-called simple waves. And the classic way of seeing this, which you find in a lot of textbooks, introductory PDE books, is you take the d1 derivative of this equation. Okay, you take the d1 derivative of this equation, and you get a right-hand side, which is a Riccati type equation. So Riccati, if you think of the left-hand side, the L operator, as a differential operator along the flow lines of L. So the differential operator would be like d dt because of the fact that the t derivative of L is 1 by this. Then this basically tells you that along the characteristics, you have an ODE that looks like y dot equals minus y squared, where y is d1 of R plus. So it such Riccati equations exhibit finite time singularity formation. That's basically an undergraduate exercise. And how do you think about this? You should think about this as singularities often form in d1 R plus for simple waves. On the other hand, R plus remains bounded because according to the first transport equation, sort of the L infinity norm, or the L infinity, the pointwise behavior of R plus is just propagated along the integral curves of L. Okay, so d1 R plus can blow up, but R plus itself remains bounded. Now, this is the absolute crudest picture of a shock wave, and it's very telling, but it doesn't give nearly enough information for the purposes of extending this argument to higher dimensions. And as it turns out, it's not really a great setup for understanding the sharp picture of what the maximal development looks like. Okay, so this is just like if you want it, it's just a proof that something's going to blow up in finite time, typically. Okay, so let's take a look at this, what's going on in more detail. So for this to actually happen, so if you want there to be blow up, basically you need this coefficient f prime evaluated at this Riemann invariant r plus. This should be non-zero. Otherwise, the right-hand side will be zero. And you might ask, when does that happen in fluid mechanics? So when is this not zero? That's called a genuine nonlinearity condition. And the answer to that question is it almost always happens. There is only a single equation of state for which this cannot ever happen. Okay, so more precisely, for all equations of state except for one, there are open sets of these background constants h bar that I'm kind of using to normalize the definition of all these variables, like f of h bar 0. There are open sets of these h bars such that the genuine nonlinearity condition holds at least near the constant state where h is constantly h bar and the forward velocity is constantly vertical. So this is, for almost any equation of state, this is an open condition that's satisfied. Now, what about the exceptional equation of state? So this corresponds in the irrotational case to the evolution of a graph of a time-like surface in 1+4 dimensional Minkowski space. This is a very, very special equation. Okay, so it has all sorts of miracle properties. In particular, we don't think that shocks form, okay, for this very special equation of state. And there is recently like a spectacular low regularity local well-posedness result for this equation posted to the archive by Tataru, Albert I, and Mihail Ephraim. And if you want, they prove local well-posedness. I want to say that it was like a 1/4 of a derivative of a gain below what anyone thought was possible. So it basically corresponds to h7/4 well-posedness, or maybe it's slightly above h7/4, like h7/4 plus epsilon. I don't remember exactly. But whatever's going on with this equation, it's basically exceptional from every single perspective. And so one should not be surprised that there's no shock phenomena known to be associated to it. Okay, now what about if you get away from symmetry? What is this? What happens if this is equal to 0? So suppose you have some Riemann invariant so that if you plug it into f prime, you get 0. What does this mean in a more familiar language? So it turns out that this is equivalent to the null condition being satisfied by the linearized equation. So if you take the relativistic Euler equations and you look at irrotational solutions and you linearize the equation around your favorite background solution such that this f prime term is 0 at that background solution, then the resulting wave equation will satisfy the null condition. Okay, and for such wave equations, one basically expects that there should be global existence, at least in the small data regime. So this is this is something very special, and you have all kinds of different phenomena associated to this condition. So we're not going to talk about this. We're going to focus on the generic thing in fluid mechanics, which is where this coefficient is non-zero. And this Riccati term is active, if you want, from that point of view. Okay, so I said I want to go beyond this crude picture of Riccati blowup. And sort of the way forward for us, or a good way forward, is not the only way forward, but a very good way forward, and to my knowledge, the most precise way forward, is to use the characteristics, or if you want, use nonlinear geometric optics. So this idea to use the characteristics and the corresponding characteristic densities, which I haven't put on this slide. I mean, the basic idea that you should study the flow with the characteristics no doubt goes back to Riemann. But Fritz John was one of the first people to really understand the relevance of the characteristics and their densities in multi-speed problems. And so he had a certain point of view that he took in his papers in the 1980s, where he was understanding singularity formation for 1+1 dimensional hyperbolic systems, for much more general systems than had ever been treated. And his point of view from those papers was like the starting point for this way of thinking. And I believe it's that way of thinking that Christodoulou took up that led to the way he thinks about shock waves. And that led to his 2007 monograph. And so that's what I'm going to talk about now. So it turns out that in 1+1 space-time dimensions, everything is just so much easier, even the method of characteristics. And in higher dimensions, even the basic equation that defines the characteristics becomes much more complicated. Okay, but in any case, what are the characteristics? In 1+1 space-time dimensions, you can define a coordinate so that at time 0, it's actually equal to -x. So here by -x, I mean like the Cartesian x1, there's only one space variable. And then LU equals 0 means you are transporting U along the L direction, where L is, this explicitly given vector field, well, semi-explicitly, the way I've written it. Okay, and so this coordinate U, you can call it or this function, you can call it an iconal function. It will turn out to be a solution to an iconal equation, even though this is not the traditional iconal equation that, as you know it. This is a simple transport equation, and again, you can only get away with this because you're in 1+1 space-time dimensions. Or you can also call this U a characteristic coordinate. And let's pretend, without worrying about the details for now, those details matter a lot, I assure you, but let's just pretend that you can go back and forth between TU coordinates and TX coordinates. Let's call TX coordinates the rectangular coordinates, and TU coordinates the geometric coordinates. Okay. And let's call DDT and DDU the corresponding partial derivatives. Now, what about the vector field L? So LT is 1. If you take the T derivative of L by construction, you get 1. And if you take the U derivative, or sorry, if you apply L to U, you get 0 by virtue of the definition of U. So that means L is ddt in these coordinates, because if you apply it to T, you get 1, you apply it to U, you get 0, it's got to be ddt. So actually, L in geometric coordinates has the simplest possible form. It's just ddt. Even though in the rectangular coordinates, so this d1, I guess you can think of as the same thing as dx. Sorry for switching the notation back and forth. Even though in rectangular coordinates, L looks like this, in geometric coordinates, it looks like this. Okay. So here's remember, what is simple isentropic compressible Euler flow look like for in one space dimension? It's just L r plus equals 0. So in geometric coordinates, it's just the T derivative of r plus is 0. It does not get simpler than this. And if the data are called r plus circle, which I can choose to think of as a function of U, remember U is like -x initially. The minus sign is just convenient for orienting the pictures. There's nothing fundamental about this being -x. Could have been +x. But you just immediately write down the solution. The solution r plus of TU is equal to the data evaluated at U. This is what the solution looks like in geometric coordinates. So in particular, the solution is smooth. It's T infinity if the data are. So you don't see any singularity in geometric coordinates. And of course, this basic phenomenon has been well known to the hyperbolic conservation laws community for a long, long time. But they just don't usually take this point of view because they're usually asking different questions. Like that community knows singularities are going to form and they just want to study the weak solution. Whereas here, in this world, we're talking about the breakdown of smooth solutions and what that looks like in higher dimensions and the structure of the maximal classical development. And for those questions, this point of view becomes very, very helpful. In fact, honestly, it feels essential. Okay, but maybe I'll make that more clear in the coming slides. Okay, so if you go to geometric coordinates, there's no singularity. It's just smooth. You've unfolded the characteristics if you want. Everything looks the infinity. But how do you see the singularity in the original coordinates, and what does that have to do with the density of the characteristics? What does that have to do with the geometry? So that's what I'm going to talk about now. So this is the part of the setup that goes back to Fritz John and Christodoulou. Okay, so let me define the inverse foliation density. You take the rectangular space derivative of u, and then you take the reciprocal and you put a minus sign. And if you by construction, because u is initially minus x, this mu, so-called inverse foliation density, will be initially equal to 1 by construction. So this is a measure of the separation of the characteristics in Minkowski space. So initially, this 1, this means that the characteristics are sort of equidistributed. And then the question is, what happens to this density? Now, I've been a little bit loose with the language. It's actually 1 over mu that is the density. Okay, so if the density goes to infinity, which you can think of as the characteristics bunching up or almost intersecting, that means that mu goes to 0. Okay, so it's actually mu goes to 0 that represents the singularity. Well, why do I take the reciprocal? It's just very convenient to have mu as a weight in the problem. So mu plays a geometric role of sort of measuring the inverse density of the characteristics, but when you go to do PDE analysis, it also plays the role of a weight. And it's just very convenient to work with mu instead of its reciprocal. Okay, so by characteristics, I mean the integral curves of L. And again, mu equals 0 corresponds to shock formation, the intersection of the characteristics, or as you can see from this formula, it means that the d1 derivative of u must be becoming infinite. So that means that the level sets of u are intersecting. Okay. So take this definition of mu and multiply both sides of the equation by d1 of u. And then you see that mu, the operator mu d1 applied to u is -1. And on the other hand, if you apply mu d1 to t, you get 0. And so that tells you that mu d1 is actually up to a minus sign equal to d du. So that sort of gives you, if you think about things in terms of the geometric coordinates, and you want to understand the relationship between d du and the Cartesian d1, or the rectangular d1, I should say, then the relationship is up to these two things are equal up to a crucial factor of mu and a minus sign. So in particular, if you take the commutator of two coordinate vector fields, you get 0 without doing any work. But on the other hand, if you think from the Cartesian picture, that's sort of like a non-trivial statement that this vector field L commutes with this weighted vector field mu d1. And so these properties are already important for understanding the flow in one space dimension. Okay. So basically, if you want to understand shock waves geometrically, you should study mu and understand exactly how it goes to 0 and all of those implications. Okay, so you can actually write down an evolution equation for mu. So how do you do it? I'm not giving any of these details. These are not hard calculations. So up to reciprocals and so forth, taking an L derivative of mu is just like taking an applying L to d1 of u. And how do you get that? Well, you basically take one derivative of the iconal equation. You differentiate this equation with d1, and remember that components of L depend, if you commute the equation with D1, you'll get terms where derivatives fall on this. And so the D1 doesn't commute all the way through. You get error terms. And you also remember that the operator L is the same as the operator DDT in geometric coordinates. And if you put it all together, you find that the T derivative, the geometric T derivative of mu, is given explicitly in terms of a U derivative of the solution is just equal to the initial data. And if you introduce an antiderivative, big F, of little f, where little f is the little f in the definition of L. If you introduce such a big F, whose derivative is little f, then it turns out that the time derivative of mu is equal to the minus U derivative of little f evaluated at the data. Okay, so this is, it doesn't get simpler than this. Remembering that mu is initially 1 at time 0, you can immediately integrate this equation with a fundamental theorem of calculus. Right? This is doesn't even depend on t, the right-hand side, to find that there's an explicit formula for the inverse foliation density. So mu in geometric coordinates, mu is equal to the data minus t times a function that depends on the first derivatives with respect to u of the initial data. Okay, or you can write it as a perfect U derivative if you want, which sometimes this can be. Okay, so basically, if you want to study the formation of a shock, and you want to understand, and you know that it's going to be tied to mu going to 0, then basically, from this explicit formula in simple isentropic plane symmetry, is trivial to describe the 0 level set of mu, and to connect that to the initial data. Okay, it's just you put this equal to 0 and solve for t if you want, and you find that you have a graph. So I'll discuss that in more detail in just a few slides. Now, what about the blow up of R plus when you differentiate with respect to the rectangular D1? Okay, so let's remember that there's a connection given on this slide between a D1 derivative and a DDU derivative. And the main connecting factor is exactly a factor of mu, for which we have an explicit formula. So you put it all together and you can explicitly write down a formula for the D1 derivative of R plus. It's 1 over mu, that's coming from the change of variables factor, times the U derivative of the solution. But the solution is equal to the data in geometric coordinates. And you have an explicit formula for the denominator mu, right? And so at the end of the day, you get an explicit formula for the D1 derivative of R plus, and you see that when the denominator vanishes, or in other words, when mu goes to 0, that will cause that is directly tied to the formation of a singularity in D1 of R plus, okay? So for in simple isentropic plane symmetry, you can sort of immediately see from this perspective that mu going to 0 exactly coincides with the blow up of the rectangular derivative of D1 of R plus. Okay, so this is a very important picture to have in mind. Okay, so then obviously, if you're trying to understand the singular set, if you want to say, okay, where does the solution blow up, and what does this collection of points look like in space-time? What is the singularity? What is its qualitative character? What are its regularity properties? Then it's going to have everything to do with, on the one hand, mu going to 0. On the other hand, at the end of the day, the way this theory has been set up is it's a theory in Minkowski space. So the real differential structure that is not this artificial TU differential structure that you've introduced to do math, but it's the original Minkowski rectangular coordinate structure that you care about. So basically, you have to translate from the geometric coordinate differential structure back to the Minkowski space differential structure, and that translation in general is far from straightforward. In fact, it's generally not even one-to-one. So we're going to digest that in more detail. Okay, So yeah, what about the level set, mu equals 0? Let's start with something basic. This is like the set of points in geometric coordinate space where t is non-negative. You could, of course, study the flow in the opposite time direction. It's the same problem. And the set of points in geometric coordinate space where mu vanishes is given by this graph. Okay. And you should, I mean, it's sort of instantly clear from this perspective that you can create solutions just by playing with the initial data, so that at the time of first blow up, at the the rectangular time of first blow up, the singular set, in other words, the set of points where mu is 0, can be sort of arbitrarily complicated. You can cook up your favorite initial data so that the statement, if someone says, what does the singular set look like at the first blow up time? What are the collection of u values? And even though one can make a statement about what's expected generically in the class of all smooth data, you can certainly cook up data so that the singular set is basically an arbitrary level set of some smooth function. And so it can have, in that way, arbitrarily complicated character. Now, what about the real picture in the I call this Cartesian picture, but maybe it's better to call it the Minkowski picture or the rectangular picture. In the physical space-time, what does the singularity actually look like? Not just this artificial geometric coordinates picture, but the real physical differential structure of Minkowski space. So one way to think about that is you want to introduce the change of variables map, which I'm calling upsilon just because it was called that way in earlier works. That goes from geometric coordinates back to Cartesian, or back to the tx coordinates, or tx1 as I'm calling them here. The problem is this map from geometric coordinate space to the Cartesian space, if you want, or Minkowski space, is not always injective. It is when mu vanishes, you can be sure that something weird is going to happen, and you can in principle lose injectivity. In fact, you can cook up an initial data where injectivity fails, for sure. And so you have to take great care in translating between the geometric coordinate picture and the what's going on in Minkowski space picture. And I'm going to show some interesting slides in a little bit. And this is already just for simple waves where you have only the L direction of propagation. You can take these simple waves and perturb them and put a small amount of R minus into the picture. And then there's a second propagation direction, L bar. So then you don't just have a single speed problem, you have L and L bar. And the picture becomes even more interesting, because what happens when you have a singularity, let's say in the Minkowski differential structure, you have to worry about the integral curves of L bar that emanate from the singularity. So basically, anytime you have a singularity, and you're interested in classical solutions, you know that you're basically going to have to remove the future light cone at the very least from that singularity. That future light cone cannot possibly be part of the maximal development. And the question of whether you're looking at a one-speed problem or a two-speed problem becomes entirely relevant at that point. Because if you're only looking at a one-speed problem, you can say, well, there is no L bar direction of propagation. But if you're looking at perturbations of simple waves where there's a tiny amount of the other Riemann invariant, then the other propagation speed becomes very relevant. And the null hypersurfaces, or in this case, characteristic curves of L bar that emanate from the singularities, can sort of cut off regions of space-time and actually prevent portions of mu equals 0 from being part of the maximal development in the Minkowski picture. And so I'm going to show some slides that illustrate some of the complexities that can occur. And all sorts of degeneracies can happen, including non-uniqueness of maximal developments. Okay, and all this is already in just 1+1 dimensions. And so these are the kind of things you have to be ready to anticipate when you're trying to study the problem away from symmetry. Okay, so first a bit more on the change of variables map from Cartesian, or so from geometric to rectangular coordinates, which again I'm calling upsilon. So you can compute its Jacobian matrix, take its differential with respect to t and u, and here it is, and where this f is coming from the L vector field, it's the same F. And if you take the determinant of this matrix, you get minus mu. Okay, so that tells you that you have, when mu is not 0, at least you have a local diffeomorphism coming from the inverse function theorem. And just to give an example of something simple that can be done, if mu is positive on a rectangle R in geometric coordinate space, then you can prove that this change of variables map is a globally injective diffeomorphism on that same rectangle. So, and this is the ease of this argument. This is basically a simple argument from monotonicity. This is easy in 1 + 1 dimensions, but already to understand in more than 1 + 1 dimensions, the global diffeomorphism properties of this change of variables map, it already can involve techniques from algebraic topology. Okay, so in this very simple context, sort of monotonicity gives you injectivity and ties it cleanly to mu being positive on rectangles. But in other contexts, it requires a much more interesting argument. And here's something else that's very interesting and very relevant for the so-called shock development problem. That even when mu is 0, so remember, mu equals 0, you sort of want to think corresponds to the bunching up of the characteristics. Injectivity can sometimes hold. Injectivity of this map can sometimes hold on subsets if mu equals 0, even though you definitely don't have the diffeomorphism property because the determinant will definitely be 0 there. So even though the characteristics can like bunch up on a curve if you want, you can still have injectivity. The bunching up does not necessarily literally correspond to the intersection of the characteristics. It's like an infinitesimal intersection, but not necessarily a true intersection. And in fact, the so-called shock development problem of continuing the solution past the singularity is only known to be solvable in principle when you have this injectivity. If you don't have this, then it's not even clear how you set up the problem. So this is a real issue. You can't brush this aside. Okay, so let me just give what I call a rich example. I see that I have just a few minutes left. If things are getting rushed, I'm just going to start at this. I'm going to restart the lecture next time at this point because this is too important to gloss over. But if you take a model problem, so take a simple irrotational relativistic Euler wave problem where L you just say is explicitly given by dt plus 1 + r + d1, and let's say I introduce the L bar direction even though it doesn't look relevant at this point in time, and it looks like -1. This is just a model problem. And then I take specific initial data that are odd, and in the rectangular coordinate world, it looks like this. And if you translate to U world, it looks like this because X is -U. And I restrict my attention to the interval U belongs to -1, 1, at least at time 0. This is already an interesting problem. You can solve this explicitly. Here's what R plus looks like. Here's what mu looks like. The level set mu equals 0 is, you can write it down explicitly. It is a graph in TU space. It's a graph T equals 1 over 1 minus U squared. And then here's where things become very interesting. So this is the mu equals 0 set in the TU space. Now, what if you translate this into the rectangular coordinate space? So with respect to tx1, how does this picture mu equals 0 look? With a bit of effort, you can show that the mu equals 0 is a curve that can be parameterized by u if you want. And the t component looks like this, and the x1 component looks like this. These are not hard calculations, but I think they're not so easy to do virtually. I don't think they're really worth doing. I'm just trying to show you qualitatively what's going on. So this is a, the image of as u, sorry, this should have been capital U. I wrote this as lowercase u, but this was supposed to be capital U. As capital U varies over -1 to 1, and the corresponding tx values vary over as these functions tell them to vary, you get the red and green curves on the next slide. So I'm going to zoom in, sort of show you what's going on. So as you, I think this is the right orientation. As if you start at -1 and you start decreasing u, then you go down this green curve, and now you hit u equals 0, and then you come back up this red curve, which is only partially visible because it's being obscured by these characteristics. Okay, so let me show you what's going on in this picture. The mu equals 0 is the union of these two curves, this curve and this curve. And if you come from the left, what's happening is that these pink characteristics, so these are integral curves of L, are collapsing and intersecting to order 0 on the red curve. The yellow curve is in the middle, and the yellow curve intersects both the green curve and the red curve. And on the right side, you have these characteristics, these black lines, impinging on the green curve, which is the other part of mu equals 0. And again, these intersections are happening to order 0 only. They're not real intersections. You see breakdown. There's a local injectivity of the upsilon map on each of these red and green curves, but not globally along the two. So what is happening? So this, believe it or not, is an example of non-uniqueness of maximal developments. I see that I've basically run out of time, and so I think maybe it's a good idea for me to just take 30 more seconds, and then maybe I'll start my lecture number 3 with a detailed discussion of this picture. So in my last 30 seconds, here's what I'll say. This blue curve, this is like the L bar direction, and this really doesn't have anything directly to do with this picture if you're looking only at simple plane symmetry, because there is no L bar direction. I'll talk about why you would think about L bar in the next lecture. But here's what's going on. If you only look at this part of the picture to the right of the yellow line, you will see a singularity forming along the green line by the Riccati blowup. Okay, so on the other hand, if you look at the picture coming only from the part of the picture to the left of the yellow line, you will see a singularity forming on the red line. Okay, so basically, what happens in the region to the right of the yellow line is not determined by just the portion of the initial data that lies over here. It's not determined by that. It's determined by what happens way over here, in the sense that you know, these pink lines want to collapse and make a singularity right in here. But you could also choose to ignore this region and just study the Cauchy problem in this region, and then you wouldn't see this red singularity. And so what's actually going on is that there is non-uniqueness of maximal developments here, maximal classical developments, I should say. And it's all stemming from this first intersection point where this yellow line collapses. And at this point, once in the one-speed problem, once you have this cusp where the yellow line is emanating from, you're going to have some kind of non-uniqueness, and there's no reason to prefer one singular curve over the other. They're both candidates for being boundaries of the maximal developments, and this is an example of severe non-uniqueness. And so you should be very worried about this. But what happens is, in a two-speed problem, you can have a Cauchy horizon that cuts off and saves you and forces you to eliminate the portion of the pink curves that want to pass by the Cauchy horizon. So I'm just going to stop there and see if there are a few questions, because I know it's very late for you guys.